Hello everyone, welcome. This is the class of ECE341, the makeup class. We canceled 2 classes during the strike, so now I gave makeup, and I will give another makeup sometimes later. And today we will keep working on the random variable, the PDF, CDF, PMF. Okay. Yeah, we will give some examples. Let's go to the document camera. Okay, this is a ECE341. It's a makeup class, makeup 1. We will consider a random variable x. I denote it as x. Then for x, right, we can have those functions, but that depending on the type of x. So we have 2 cases: discrete type and the continuous type. So for discrete type, we can have PMF. We denote it as Px of lowercase x or equal to the probability of capital X equal to x. Right? It's a random variable. Capital X has this lowercase x as value, then find the probability we get PMF. This definition just for discrete type. And for continuous type, for both actually, we have a CDF, which is denoted as Fx of x or equal to the probability now is a capital X smaller than and equal to x. Somehow different with the first function, right? So this function CDF can be applied for both discrete type function and discrete type random variable and continuous type random variable for both. Right, this is for both. And then for the continuous type random variable, we have a PDF. The same name of kind of files, but this is a probability density function. We denote it as lowercase f capital X. This is the name of the random variable. At x, it is a derivative of capital F according to variable lowercase x, the PDF. Right? So we have these 3 functions. And for the calculation, we know this Fx of x or equal to summation for those. Okay, here's x. Here I used some alpha smaller than or maybe equal to this x. For all these alpha, here's a Px of alpha. Or for continuous case, it is very integration from negative infinite to this x. Here's a Fx of x dx. Okay, I have 2x. They may confuse. Here I use alpha for this. Alpha for this variable. Alpha. Fx alpha d alpha. Alright. Yeah. So the relation. If you have CDF, you can find. CDF can be obtained from PMF and PDF by this formula. And we also have some properties about these functions, like we know Px of x, they must be non-negative values. The summation of all of these Px of x will be 1, and similar for Fx x, the PDF, it is also value larger than 1 or equal to 1, and the integration of Fx of x dx it will be 1. Similar property. And here we have one more. The px of x will be smaller than or equal to 1, at most 1, no more than 1. But for PDF, you can have a value larger than 1 because the integration is 1. So every value of fx might vary, might even higher than x, higher than 1. And for CDF, we have fx of negative infinite is 0, fx positive infinite is 1, and fx of x is increasing. That means if x1 smaller than x2, we will have fx of x1 smaller than or maybe equal fx of x2. Alright. These are the basic definition and properties of discrete type or continuous types random variable with those functions. Now we consider some examples. Example 1. Actually, last time we already studied some examples, right? Now we consider more. In previous classes, the examples, suppose we are given the PDF, we have PDF or PMF are given, and try to find the CDF and then calculate some probabilities. Now we consider another case. Suppose we have CDF, then we start from CDF, try to find something else. Okay. Suppose random variable x has CDF as follows: fx of x or equal to some value. I will see. Say like I don't know, just any value. Say 0 if x smaller than 1, and then 0.3 if 1 smaller than x smaller than 2, and 0.5 if 2 smaller than x smaller than 3.5, and 0.7 if 3.5 smaller than x smaller than 5, and it is 1 if x larger than or equal to 5. Alright, so this is a CDF. You can see this function satisfies the requirement, the property. For negative infinite, when x is the negative side, right? Negative infinite is 0, and when x go to positive infinite, it is 1. And between these 0 and 1s, there are some values, they are increasing, right? When x increase from negative infinite to 0 to 2 to 3.5 to 5, then larger than 5, when x increase here, the value of fx is also increasing, right? So this is a CDF. Now for this function, based on this CDF, we can ask some questions, or in other words, we can know some more information about x. Like first one, we want PMF equal to 1. Actually here, first of all, you need to determine this is a discrete type or continuous type. Continuous type. Which one? I will say this one. It's a discrete. Why? You look at here. Okay, Yeah, we need to do some research before we can find this. We need to study it. Okay, so before I give this question, before this I need to ask for which type it is. For this way, you give a graph, that will be good to understand what it is. Its value is 1, then 2, then 3.5, then 5, right? 1, 2, 3.5, 5. Right? At 1, its value is 0.3. 0.3. At 2, its value is 0.5. And then 0.7. And then 1. And here, when the x is smaller than 1, it's 0. Now here, increase to 0.3 and keep 0.3 until x equal to 2. X equal to 2, it will be 0.5. Right, jumping up. And then keep 0.5 until x equal to 3.5. Looks like this, right? Similarly. So you can see this is a steer-wise, right? Looks like steer. So if you have a CDF looks like this, it is a discrete type. Right? It's a discrete type. And we can know the PMF. What's the PMF? You just check the steers. The steers, how much it jump up. So like here is a 0.3, right? Here its jump is a 0.2, and here is a 0.2, and here is a 0.3. Okay, so PMF will be looks like this. Just those jumps. At 1 we have a jump, it is a 0.3. At 2 we have another jump, is 0.2. And at 3.5 we have jump 2 again, 0.2 again, and at 5 we have another jump, 0.3. So this is PMF. You just use these steers. That is a PDF. That is a PMF. And we write it in function. PMF is Px of x or equal to. We have, okay, this one is simple. We only have two values, right? 0.2 or 0.3. So it is a 0.2 if x equal to 2 or x equal to 3.5. And it is 0.3 if x equal to 1 or x equal to 5. And 0 otherwise. Right, you choose different x. You choose x other than these four values, like here or here. Now you get 0. Okay, so this is PMF. Alright, after we have this, then we can have almost everything about this random variable. For example, we can find the probability whatever, like x larger than 3. Right, this is event, right? Capital X larger than 3, it will be what? Larger than 3. You check this one. Yeah, check the PMF. 3 will be here. This is 3. Larger than 3, so we have two values, 3.5 and 5. So the probability, it is just summation of these two. So we write the Px at 3.5 plus Px at 5, which is 0.2 plus 0.3 is 0.5. Yeah, we can also find like we can calculate like a probability of x equal to 5 under the condition x larger than 3. Probability with condition, remember? Then this will be the probability of x equal to 5 intersection with x larger than 3 over probability of x larger than 3. Larger than 3 is the condition. Then the numerator x equal to 5 and x larger than 3. That is just x equal to 5. So we have, this is the probability of x when x value is 5. And the denominator is this one, we already calculated, right? The first part, so it's 0.5. Okay, the numerator value is x equal to 5, the probability is 0.3 over 0.5, which is 3 over 5 is 0.6. Yeah, we can have this calculation. We can calculate, find more if you want, right? Suppose you know these values. Yeah. Okay, this is one example. Any question? You can answer me right now. So this is why I prefer in person in the class to have the class. Now we can have questions, right? Here I can just I speak myself. I don't know what's your questions, but it's fine. Just makeup, right? We need it's hard to find the time, like so that all of us can sit down for a lecture class in classroom. So okay, now let's consider another example. Example 2. Now we consider a continuous kind of a random variable. Random variable x has CDF. We still start from CDF, but now this time is a continuous case. It is fx of x equal to we have two parts. It is 1 minus e to the negative some lambda x, lambda x is here, lambda x if x is larger than or equal to 0, and it is 0 if x is smaller than 0. Okay, actually we have name for this one. This is a exponential distribution. Right? It's a way to distribute the probability, right? This is exponential distribution. Okay, then we can try to find something. The first one, I want to find the PDF. Wait, I put the K here. Alright, I put the K here. And other than PDF, I also want to find the K equal to 1. Can I have a K, different K? Yeah, we should try. Oh, it doesn't matter. It should be 1. I just think maybe it is yeah. We want to determine this one and this one, PDF and the K. And secondly, we can find some probability, like we want to find the probability of x larger than 1, probability like x larger than 4, and the probability of 1 smaller than x smaller than 4. Yeah. And okay, here we have interested some factors interested. We want to find the probability of x larger than some s plus t over the condition x larger than s. Yeah, okay. Let's see what happened. For first one, PDF fx of x, it will be the derivative of CDF. Right. So actually here it doesn't matter we know or do not know k, we can do this calculation. So we get 1 take derivative get 0, and here take derivative, it is lambda, negative lambda times negative k, it's lambda k, and e here is negative lambda x, right? And for k, now we can use some properties to determine that. When k, we want this one, f x of x. I can give a graph to see how it is. This side should be 0, right? For negative x is 0. And when x is positive, it is 1. Okay, when x is 0, I get 1 minus k. Suppose this is 1. Here's a k. So it looks like this, right? When x is 0, this is 1. So 1 minus k. This is 1 minus k. And then increase. When k go to infinite, this term turns to be 0. So it looks like this. Oh, here I have a jump. The jump, I cannot have the derivative. I still can take the derivative, but this one cannot have derivative. So I have to let k equal to 1, right? I have a jump. Therefore, continuous type, we cannot have jump in the CDF, right? So here k must be 1. K must be 1. No jump. Here's a jump. A jump. No jump is allowed. Is allowed. No jump is allowed. No jump is allowed for continuous. Continuous random variable. Yeah. So k must be 1. K must be 1. Now when k is 1, here's no jump, right? This point is 0. When k is 1, this is 0. K must be 1. You can also calculate here the integration of x dx. This should be 1. This should be 1. So for this one, it's 0. For x larger than 0, for x smaller than 0, right? Smaller than 0, you take derivative, you get 0. Larger than 0, you take derivative, it is this one. You get this one. Okay. Then the integration should be 1. So we have this is fx, right? Fx. Take integration. We have lambda k times 1 over negative lambda e to the negative lambda x, and x round from 0 to infinity, right? This integral, because the integral from negative infinity to positive infinity, but this side is 0 after x is positive. Only for positive x we have this part. So this is just integral from 0 to positive infinity. This will be this cancel, right? We only have k here, negative k here, and inside is e to the negative lambda x now is infinite minus e to the negative lambda times 0. This is 1. This is 0. So this is a negative k times negative 1 is k. So k is 1, right? Same thing. So we can have k equal to 1. Alright. So k is 1. K is 1. K is 1. And fx is this one. This PDF is this one. Alright. After we have PDF, then we can calculate those probabilities. Right? We can calculate those probabilities. Okay, second part. The probability of x larger than 1 equal to Okay, now we have several ways. The first way is just integration of these PDF, right? It is just this one, larger than 1. No, sorry. It's larger than 1 to positive infinity, fx of x dx. But we know relation between fx and the PDF. We know fx of x equal to negative infinity to x. This fx, I use alpha here, d alpha, right? It's different with this x. Okay, so we know this one, right? So we know this one, fx x dx. It is the integration from negative infinity to positive infinity minus integration from negative infinity to 1. Make sense? This integration is from 1 to positive infinity, and here this is from negative to positive infinity, and minus from negative infinity to 1. Use this one, subtract this one, you get from 1 to infinity, right? 1 to infinity. So this is just this one minus this one, and this is fx infinite, positive infinite, and this is fx of 1, right? Negative to x integration, negative to 1 integration. So negative to x is fx. Negative infinite, you just replace this x by 1, you get this. And similar, you just replace this x by infinite, right? Just is this one. So now to calculate this one, you have two functions, two methods. One is calculate what it is. This one you can find the answer. The other way is, because we know CDF, so we can use CDF, this one minus this one. You got it? Yeah. Okay. So we can use this method. This should be 1, right? This should be 1. And minus fx at 1. We know what is fx, right? Fx is 1. Is 1 minus k, we know is 1. Then e to the negative lambda x is 1. Right? Lambda times x now is lambda times 1. Okay, so this one gave us 1 minus 1 cancelled. This is a plus, positive, e to negative lambda. Alright, yeah. So we can have the answer. Oh, here I suppose lambda is a constant. Lambda is positive constant. Yeah. So we can have this property, this one. Of course, its value depending on lambda. If lambda, you know lambda, then if you know lambda, you can have exact value. We do not know what it is, I just leave it here. Then similar, we can calculate x larger than 4. X larger than 4. You still can do a integration based on the PDF, but now we can calculate. This is a x run from negative 4 to infinite, right? So it is fx infinite, positive infinite, minus fx of 4, right? Similar like here. We now we start from 4 to infinite, right? Then we can use negative infinite to positive infinite, and here's minus negative infinite to 4, right? You this one, subtract this one, you get this one. Yeah. Then from 4 to infinite, so infinite minus 4, right? Fx. And similar, this should be 1, and the second is e to the to 1 minus e to the negative lambda times 4 lambda. So this is e to the negative 4 lambda. Alright, and then we can have another one. Okay, probability of x between 1 and 4. Okay, similar. This time you can also calculate in this way: 1 to 4 fx dx, or just fx at 4 minus fx at 1. And subtract these two. Okay, then we can have this one is 1 minus e to the negative 4 lambda, and the second is 1 minus e to the negative lambda, right? 1 minus 1 cancel this negative. This is a positive. I put positive in the front. I have e to the negative lambda minus e to the negative 4 lambda. Right. So we have the probability of this one. And the third question, I have asked for the, okay, this one, conditional probability, right? This is a 3. We want to know this probability. Probability of x larger than s plus t over condition x larger than s. Here s and t are some value, s, t, positive value, right? Larger than 0. Okay, so what it is? This is the probability. Is numerator will be an intersection of two events: x larger than s plus t and x larger than s, right? Intersection of these two events over this one as the condition is a p of x larger than s. Okay, then we do calculation. Before calculation, I can cancel. I can remove this, right? Larger than 4 minus t, 4 plus t. This is x. Some s plus t. Larger than these and larger than s. The common area is just this part, right? The common area. So the intersection, it is just the first one. So it is a probability of x, probability, x larger than s plus t over probability x larger than s. And then we can calculate this one. We use CDF to calculate. This will be CDF, f x of positive infinite minus fx s plus t, and the denominator is fx infinite minus fx s, right? Question? Yeah, you can see larger than s plus t, right? So it's from s plus t to infinite. This side is infinite, right? So the infinite minus this point. And denominator is larger than s, from s to positive infinite. So it's positive infinite, this value, minus the value here, right? The interval is here. So the upper bound minus lower bound. Yeah. Okay. Then just plug in what is fx. It is 1 minus e to the negative lambda times x. Now this is a positive infinite. This is the first one. And second one, this is a 1 minus e to the negative lambda. Here's s plus t. And denominator is still this one, right? 1 minus e to the negative lambda times positive infinite minus 1 minus e to the negative lambda, here only s. Okay. The numerator 1 and 1 cancel. We have these two. This is positive, I put it in the front. E to the negative lambda s plus t, and the minus. Okay, this is infinite, so this is 0, right? Negative e to the negative infinite. This is 0, so it is minus 0. And the denominator 1 and the 1 cancel, and this is positive, I put it in the front. This is negative, but dissimilar. This is 0, so it's minus 0. Okay, So this is e to the this fraction. It's a fraction of this one over this one, and we can cancel this s, right? Lambda s term, they can be cancelled. So e to the negative lambda t. Oh yeah, this one. Okay, so we have this one, and actually here we have a important, interesting property for the exponential distribution. And we have this one, right? And you can see what it is. You compare here, like here. This is the probability of this one, okay? And similar, we can have probability of x larger than t or equal to e to the negative lambda t. You see? Now this is larger than s. You get here's s. Then here's a t. Now here's a t, right? You just replace this s by t. Then here will be t. So we get this. Now you compare. Are they same? Yes, they are same. So we have a result like this. Probability of x larger than s plus t on the condition x larger than s or equal to the probability of x larger than t. If x is we call not is we call it this obeys exponential distribution. If x obeys exponential distribution, then we have this property. You can see if x already larger than s, under this condition x larger than s plus t, you have a probability. This probability is the same when with the event x larger than t. So you can think like something is working, right? You can consider like x. You already know x is larger than s. Then x give even more values, go to t, will be as same as you just had x without any condition, just go to t. Right? If you think this s and the t are kind of times, so previous result were not were not change the later result. Right? The probability. So we'll call this is a memoryless property of this exponential distribution. Its behavior is like no matter what is the previous condition, what is the condition doesn't matter. You consider that condition, you remove the condition. So how much increase in that condition? Then just use that t, right? Here's based on the condition, you have more values here. Then you just use this value, you calculate the probability. So the behavior is like the variable were totally forgot what is the condition. That's a memoryless property. Called this a memoryless property. Alright. Any question? You will reply. Alright. Now we consider another example. Example 3. We still use a random variable, but we consider a high dimensional case, or we say second dimensional, two-dimensional case. Remember we have an example like the phone call problem. Phone calls. Then we separate as two kind. One kind is we have the digital call or the traditional call, right? Digital call, digital call or traditional call. Digital call or traditional call, right? Yeah, and we can have the call with a short call, medium, and long call, right? Yeah. Okay. Long call, medium call. This is a short call, right? And then we can have the probability. We gave some different probability here, like for example 0.2, 0.1, 0.1, 0.2. This is totally 6, right? Totally 6. I need another 0.3, 0.1, for example. Now totally is 1, right? That will go 2. This is a 6, 5, 6, 7, 9, 10. Yeah. Okay. So suppose we have this. This is the distribution, how the probability distributed, right? Okay. Now define x equal to x1, x2. x1 equal to 0 if we have d in case d, and x1 equal to 1 in case t, and this is t, and x2 equal to, okay, I just write 0, 1, 2 in case short, medium, long. We can define x in this way, because now we have two factors, right? Two factors, two-dimensional. So that means this d is just according to x1 is 0, t is x1 is 1, right? Makes sense, right? So now we have this. This is x1, it will be 0 and 1, and x2, it will be 0, 1, and 2, and the probability will be here, 0.2, 0.1, 0.1, 0.2, 0.3, 0.1. So we can have this. And then similarly, we can do some calculations. Like here's I add them together. I have 0.3, 0.3, 0.4. And here in this direction we do the summation. I have 0.6, 0.4, and totally is 1. Right, we can have this. And for this one, now we can write it in a function way. We can write this part in function way. In function way. This here, okay. In function way. So we have first one. We have the PMF. Okay, of course, this is just PMF. This is discrete type, right? Discrete type. Of course, this is discrete type. Right? This is discrete type, not continuous. Discrete type. So we have PMF. But this PMF, we need two variables. So we have f. You can write x1, x2 of lowercase x1, lowercase x2. In this way, it will be, now we have 1, 2, 3, 4, 5, 6 values. Something can merge, right? This 2.2 can merge together. 0.1, 0.1, 0.1 can merge. Okay, so it is a 0.1 if x1, x2 equal to, we have these three cases, right? So this one is, this is 1, this is 0. So so equal to 1 0, or this one, so x1 is 0, x2 is 1, x1 is 0, x2 is 1, or this, x1 is 1, x2 is 2, x1 is 1, x2 is 2. This is for point 1. And point 2, if x1, x2 equal to, similar, right? These two cases, so 0 0 or 1 1, 0 0 or 1 and 1. And then point 3, just this one is point 3 if x1, x2 equal to x1 is 0, x2, x1 is 0, x2 is point 3 is 2, and 0 otherwise. All the other cases, any other x other than these values, any other x1, x2 is just 0. So we have PMF, sorry, this is P. We have PMF in function way, it will look like this. You can think this is kind of a graph way, table way. This is table, this is table. Yeah, we can write it this way. And then how about this part? Remember what are these? We call these are the marginal distribution, right? Marginal distribution. This part in the middle, this part we call it as a joint distribution. This part, this is a joint distribution. Joint distribution. Actually, second order, second dimensional, two-dimensional cases is also very useful in a lot of cases. So I give an example like this. The idea is as same as just one-dimensional. The idea is similar, right? Just you have more numbers, more values here, and more change, right? So in the middle, this part is a joint distribution. They give all the values for all the possible results. And here's a marginal, like this is a marginal distribution of x2, right? When x2 is 0, it's probably the point 3. It is a combine of all the possible x1, right? Combine of them. This is similar. When x2 is 1, and x1 could be any value, the probably is 0.3. So this is a marginal distribution of x2. x2 is changing. x1 could be any. And similar, this one, this part, this is a marginal distribution of x1. Similar with that, x1. Yeah. And here we can also have the marginal distribution. Marginal distribution we have px1 of x1. Yeah, it is just as same as a one-dimensional case. It is okay. For x1, we know its value will be 0.4, 0.6, or 0. If here's x1 equal to 0, this is x1 equal to 1. This is others. Okay. And px2 of x2, this will be this one. So it's a 0.3, 0.3. Oh, I have 2.3, so I can merge them together. Just 0.3, then 0.4. Here's a 0. Here's a 0.3. We contain two cases. So if x1 equal to 0 or 1, and here if x1 is, this is x2. X2. If x2 is 2, 2 is 0.4, and all the others. So we have marginal distribution. Yeah. And after you have these, of course, you can do some calculation. You find some probability, some conditional probability, as we did before, right? Okay. Alright, that's all for today. See you next time. Actually, see you on Monday. Monday we will have a quiz. Alright, yeah, based on the lectures today and the previous 2 lectures. We will test the knowledge about the random variable, the CDF, the PMF, and the PDF. Okay, bye bye. Have a good weekend.